In the last video, we discussed the need for a standard in the layout of the positions and orientations of the multiple views in a drawing. So the rule we'll use is called the third angle projection. So why is it called the third angle and what is it? If you have a rectilinear coordinate system in the space, you can divide the space into the 4 quadrants. There's a convention of naming the quadrants as the first, the second, the third, and the fourth in the counterclockwise direction as shown in the figure. Imagine you're standing and looking straight on the front plane as shown in the figure. If an object is placed in the first quadrant and its image is projected onto the front, plan, and profile planes, it is called the first angle projection. If the object is located in the third quadrant space and is projected, it is called the third angle projection method. The second and the fourth projection methods are not used. The first angle projection method is used in some countries, such as many European countries, but we use the third angle projection as a part of our ASME standard. So we'll focus only on the third angle projection. So how does it work? It is best explained by using the glass box analogy. All projections in engineering multi-view drawings use orthographic projection. In other words, the object is projected onto the projection plane in the normal direction as illustrated in the left figure, in the third quadrant space, and the images are projected in the same way onto the front, profile, and the plan planes as shown in the figure on the right. This animation illustrates how each image on the glassbox wall is projected from the object. Imagine the third quadrant space is a box made of 6 sides of glass plates, and the object is contained in the glass box. The image of the object is projected and etched onto the 6 sides of the glass box as shown in the figure. You are standing outside of the glass box, looking at the object through the particular plate marked as front. Now, the glass box is cut along the corner lines, and all plates are unfolded onto the fixed front plane as shown in the figure. Assume each image is etched on each glass plane, so each image moves and rotates with its plate. Notice how each plane swings relative to the front plane, and how each view changes its orientation as the glass wall unfolds to the front plane. Here's an animation of a glass box being unfolded around the front plane. Here's a figure of all 6 unfolded plates onto the front plane. Notice that the top is above the front, right is on the right side, left is on the left side, and so on. Also notice how each view is oriented after it is rotated and placed onto the plane. Again, same layout of the unfolded planes viewed in the normal direction without the glass box boundary lines. This is the standard layout of the 6 views, and this is how the multi-views are displayed in the engineering drawings. There are the front view at the center. The top and bottom views are vertically aligned, and the left, right, and back views are aligned horizontally. These alignments are extremely important in the engineering drawings. In the drawings, there is no label for the views. The views are identified by their relative locations and the layout. So please do not add a label to each view. In this drawing, only 3 views, front, right side, and top views are shown, and the views are aligned horizontally and vertically. So the width of the front view and the width of the top view are the same. The height of the front view is the same size as the height of the right side view. The height of the top view should match the width of the right side view. If you draw a horizontal line from the hole center line in the front view, it matches the center mark of the hole in the right side view.